Okay, sorry for the delay. Everybody hear me? All right, I'm going to take off the mask here. And one of the distressing things about the pandemic is how many people have told me I look better with the mask. Thanks very much, Vanita, for putting together such a lovely program. We're going to change directions here from quantum research to quantum education for this session. I'm going to tell you a little bit about the general situation for quantum education at the master's level and describe our experience at Wisconsin with our master's program. I've been very fortunate to have a great staff here, which has helped us get the master's program up and running. So let me give you a little bit of a personal timeline. At Wisconsin, we started doing research in quantum computing and related areas about 20 years ago and started putting out PhDs maybe in 2005 or so. And they were doing fine, but then about 5 or 6 years ago, we noticed that they started to do better than fine, that there were bidding wars for the PhDs happening, not something we usually see. And this got us excited about educating more people in quantum. So obviously that 2005 event was related to the beginnings of big programs at some of the larger companies. And the idea of also then educating students at the master's level was that as programs, industrial programs get bigger and move from the research phase to the development phase, then groups get larger and you need everybody. You need not just PhDs, but you're going to need master's students, undergraduate degrees, and so on. And so we decided to do that. And in 2019, we started our program. That's when we first admitted students. And since that time, things have continued to take off. You can see that from the 2019 level of job postings, there's been a factor of 3 or 4 increase just in a few years. So certainly, I think not only do we feel pretty confident that we can place our graduates, but I think there's a lot of room for other programs as well. So here are just some of the master's programs in the US that I'm aware of. I apologize if I'm leaving some out here. So Duke has one, which has started this year. This is more in electrical and computer engineering and has both software and hardware track. You can see also the tuition there. I put that in for a reason that I'll talk about later on. The thing which distinguishes various programs is partly whether they're in one department or not, or whether they're interdisciplinary. This is a big decision that people have to make about a master's program. It's difficult to organize interdisciplinary programs. This is something that we decided to avoid, and some other places have decided to avoid, but some other places have also bitten the bullet and tried to organize this across departments. There are various degree titles here. There is, for some places offer a virtual option. The interesting thing about the local program here, which has just started, Rhode Island, it's unique, I think, in that it is integrated with the undergraduate program so that you can do a 5-year program and get both a bachelor's and a master's degree. It's unique as far as I know in that regard. Our program was just in the physics department. Partly this was because there wasn't a lot of quantum activity outside the department. That's changed now, so we might also rethink that. Other things that, other variables for different master's programs, how much outside activity there is, that is internships and so forth. Whether it's 1 year or 2 year, this is a big decision to make. We've gone with 1 year, thinking that we'll try to get people quickly through into the job market, or if they want to go to a PhD, that's also less of a time commitment for them. But that makes it a very intense program, quite difficult and more difficult to get a good research project through during that short time period. we found that it is actually in some ways an advantage. The students, we put them all in one office. There's a single office for them. They can sort of bond together and get through that intense 1 year helping each other out. Apart from master's programs in the US, let me just mention a few other programs that have recently started here or internationally. So these programs, I think, were started already a few years ago. In case of Waterloo, I think some years ago. ETH Zurich, Delft, and Munich have programs in this area. Waterloo is interesting in that it's very spread out across departments. It's not specifically a master's program, actually, or more of a certificate program, actually, although I have it under the master's program. There are certificate programs. This is also something people can consider. There's a long-standing MIT program, which is all online. Chicago has started a program. I understand Dartmouth also. Quite a number of universities have done things at the undergraduate level, established minors programs, or simply a suite of courses that undergraduate students can take. That's been done at a number of different places. I was just hearing this morning about the one at Pittsburgh. Other master's programs are being developed. I just reviewed a planned program at Stony Brook. The first quantum PhD program that I know of in the world, actually, just started this year at Harvard. So that is the quick overview of PhD of programs mostly below the PhD level in the US and internationally. Let me switch now to talking about our experience at Wisconsin, particularly in case other people are thinking about establishing master's programs. I hope that some of the things that we have done will be of use. So we decided, as I said, to do a 1-year program. So it's 1 calendar year. So that's 3 semesters that you have to go through all the way through from fall to summer. And we have a mix of classroom instructions, a lab course, and research. It is based in a single department, which is simplifies things, but students can take electives outside. It's a self-financing program. That is, we have to pay out of the tuition money from the students for all the administration, all the additional expenses that the department incurs, including faculty teaching time and so on. This means that it's expensive, at least according to my way of thinking. And this high tuition, I think, is not good if you want a diverse student body. This is a sort of structural obstacle to diversity that I think is very important. I talked a bit about the tuitions for other programs. I'd just like to point out that the tuition at the ETH Zurich, certainly one of the world's leading scientific research universities, is $790 a semester as compared to our $50,000 for a year. And if you can have tuition done like that in a more socialist kind of system, then I think that is a big step towards having a more diverse student body. So we're trying to get students into the job market quickly, but we've also found that many students are using this more as a springboard towards a PhD. And so we try to serve those students as well. So there's a wide variety of electives that they can take, not only in the physics department, but also outside. And we try to offer them help with both in their job search and with PhD applications. We try to bring in speakers from industry, both online and in person. This helps with networking and also just gives them an idea of what kind of skills they need and how to apply for positions in university. We take students not only from physics backgrounds, but also from computer science, electrical engineering, in fact, all STEM backgrounds. This creates an interesting situation with respect to educating them, which I'll talk about in a moment. A few things we do are try to do intense advising and teach them quantum mechanics in the first month. Let's see, I'll skip about the lab course. I'll talk about that a bit later. People ask me about statistics. So we started in 2019. I think we were ahead by 2 years compared to other programs in the US. What's been the demographic statistics here? Well, in 2019, we had 38 applicants. We took 29 of them, which is a pretty big fraction. 12 students responded they would come, only 8 arrived. This is a difference between master's programs and PhD programs that I wasn't expecting. Usually when students say they're coming for your PhD program, they do show up. Master's programs, they're kind of still looking around. Maybe they'll do something else. So we need to take that into account in the future when we decide how many students we're going to admit. If you look below here, the number of applicants has increased pretty quickly in the last 3 years. We had 76 applicants this past year, and we took 38, and we've got a class now of 14 this year. And we have, in fact, graduated so far 16 students, first class of 6, and last year class of 10. So they're now on the job market or in PhD programs. The mix between domestic and international, for some reason, the international students have sort of increased and the domestic students not as much. I have the feeling it seems, at least anecdotally, that the sticker shock is discouraging, I think, some of our domestic students, and that's something we really have to figure out how to do something about. Diversity hasn't, I think, been that great. The percentage of applicants that are women is only about 20%, and in fact, in all of these 3 years, we've only had 2 women actually come. We have them studying now. Okay, so the goals of our curriculum, as I said, we're trying to educate students from all STEM backgrounds. We tried to give them well-rounded introduction, both software and hardware, try to get them through in 1 year. So we do have an option for a second year. Some of the students find the program too intense and take a somewhat reduced course load, and then they can go for a second year and finish up. We have a few students who are doing that. Probably about 10 to 20% prefer to go on and do that second year. We want to give them a significant lab experience. I'll talk a bit about the lab course in a moment. And we want to provide significant exposure to research. So here's how we designed the curriculum originally. So the basic introductory course is this Physics 709 course here. And this is the quantum mechanics of two-level systems, quantum circuits, algorithms, a pretty standard kind of Nielsen-Chuang type course. The tricky thing is to give the students some kind of introduction to quantum mechanics in the very first month of this course, so the first quarter of the course. So this means that they have to have some linear algebra before they get there, so they know how to multiply 2x2 matrices, and they know what a Hermitian operator is, a unitary operator. And then we teach them things like tensor products and how to string together unitary operators to make a quantum circuit and so forth. The thing which you do have an advantage of, is that you don't need to know that much quantum mechanics to get started in quantum computing. So in this first semester, they never have to solve a differential equation. You don't have to do Schrodinger's equation with piecewise constant potentials, anything like that. So this means that you can get students started pretty quickly, even if they haven't had a junior or senior level quantum mechanics course in an undergraduate career. The second thing they have to do is a Physics 701, which is a 1-credit course. And the faculty come in and tell about the research that's going on in the department. And then the last part of the course is the students tell us about their interests, and then they form into teams to do a research project. The problem with which this solves is the scaling up providing research opportunities for students. This is very tricky. If you only have half a dozen, which is what we had in the first year, then you can just sort of pair them up individually with professors. But if you're going to have 15 or 20 students, that's too many projects and it's too much faculty time. So we're forming them into teams, 2 to 3, to cut down the number of research projects and reduce the burden on the faculty. Then they take another quantum mechanics course and other electives. Then in the second semester, then you do have to solve a few differential equations. You need to learn about density matrix decoherence, quantum control, and also hardware. And then again, they're doing electives. And then the students do research projects starting in the spring semester and continuing on into the summer where they conclude and write up a report. The lab course, that is focused on quantum hardware and matched the faculty expertise in our department. I'll say a bit more about that in a moment. Let me skip this. Instead, go on to the lab course. So this is an intense lab course. It's an 8-week course, and the students have to do one lab every week, basically. So these are the labs that we're currently doing. There is a neutral atom lab where they actually construct magneto-optical trap. So this is something that we have developed from scratch. It's actually not quite done. So we weren't able to offer it in the past summer, but it's now being finished up. And so the students will be able to do that in this coming summer. Single photon experiment, trapped ion experiment. They don't actually trap atoms here, but they do trap dust particles and can observe the trap oscillations. And then we do an NV center experiment. So this was actually developed in-house. We have an expert, Shimon Kolkowitz, who actually came from Amir Yacobi's lab. And so he actually got that up and running quite quickly. And that has been one of our very successful labs. You can also buy this lab off the shelf from, I think it's called China Tech. It'll cost you about $50,000, and I understand it works pretty well. But we've been happy with our own. So there's a Josephson Junction lab. The Bells Inequality Lab is also one of the student favorites. That we're probably going to upgrade this year to not only demonstrate entanglement, but also be able to measure some measures of entanglement, including concurrence. And then we have some laser experience for the students. And then also under the lab is a remote lab that you do using the online quantum computers provided by IBM. The students also seem to like that a lot. So that's been where we have put that part of our education of the students is in the lab course. Okay. So as I said, I wanted to try to make our experience useful to others who are thinking of doing things along these lines. So I pretty much designed and planned this master's program. And the big mistake I made was in not giving sufficient emphasis to research. It turned out that all of the students were excited about research, and it turned out, the reasons they came to Wisconsin particularly was because we have a very active research program in quantum. And so that meant we had to do things on the fly, which we did the first year. And during the course of that first year, I was also talking a lot to employers, and they also emphasized that research was important. They were fine with the classroom experience we were giving the students, but they're more interested in softer skills, if you like. Can a student plan a project? Can they carry it to completion? Can they work in a team? Can they communicate the results? All of these things that the research experience gives them that the classroom instruction does not. So we were able to use our directed study course to handle this. And it went okay in the first year just because there weren't so many students. So they say it's difficult, though, to make this part of the project scale if you're going to do, let's say, 20 students. So we are going to a model of 2 to 4, 3, 4 students working on a single project. And we organize this in the fall by pairing them up with an advisor by the end of the fall. And then the projects start in the spring and end of the summer. In the few cases, we're able to pair students up at the beginning of the fall, and they're able to use a whole year and get their project done. So this will reduce the faculty workload, which I think was a little too high with the individual approach. Even so, this takes a lot of faculty time. One of the things I found when I was chair of the department and dealing with the higher administration was that they seemed to assume that there was this sort of bottomless well of faculty time, and you could just give them more things to do. And a master's program does give them more things to do, and that well is not bottomless. You have to really think about that. And so we have to think about how to compensate them in some way, and we do have some money to do that because there is tuition money coming in. But that's an important issue that anyone who is thinking about a project of this type has to consider. What about other lessons having not so much to do with research? So the diversity issue, I think, is a tough one. And I think that is limited. I think the most difficult problem is financial. Students who don't come from a background where their parents are going to be able to pay for this or where they feel comfortable taking on a large loan are going to be deterred by high tuition. And I'm actually not allowed to do much about that because the university insists that this program pays for itself. But we have to think about how to perhaps fundraise or have other ways of reducing the financial burden. We have tried doing targeted marketing towards underrepresented groups and women, and I'm hoping that that'll help us to enroll more women and underrepresented minorities. The other problem is this very diverse level of student preparation. I've already said a few words about that. One thing that we started to do this past year was to have, once the students accept and they're going to come, to set up webinars telling them what it is they're going to need to know when they arrive. And we also have a written guide, things they should be reading. This is mostly linear algebra, probability statistics, and maybe some kind of a gentle introduction to quantum mechanics. When they come, we have to advise them very, very intensely because their preparation is such that one size doesn't fit all, and they need to talk to an advisor and tailor their program to their own capabilities and interests. As I said before, and I guess I will repeat, you need to take advantage of the fact that they don't need to know a ton of quantum mechanics to get started in quantum computing. This is the only thing really, I think, that makes a one-year program possible. If you had to spend a semester bringing them up to speed on all the physics they were going to need to know, then it just wouldn't work, I think. Finally, we have found that team building in general has been very important for our students. So it's a fairly small number of students, and the first 2 years we have found that they did build a community up pretty well, and they helped each other out a lot. So the stronger students would take the weaker students maybe under their wing. They got to know each other pretty well. We have social events when they first arrive. They're all in orientation together. A dedicated office space turned out to be, I think, maybe the single most important thing. And I was very grateful to the physics department for putting that aside for us. Another tricky thing is just how to mesh all the courses with the other courses with the needs of the undergraduates and PhD students that are there. So these students come through in 1 year. That means they have to follow a pretty strict schedule, and not all our courses are offered every semester and so forth. So this is a very this is another kind of thing that you have to think about in advance if you're thinking about starting a program of this kind. Other things, the instructional labs. If you have a good instructional lab program, particularly at the graduate level, then of course you can leverage that. But we still found that we had to do quite a bit of development. We hired graduate students to develop labs. They had to be supervised by faculty members. So this is something that you need to plan for in advance and pay quite a bit of attention to. We found that if the lab course was in the summer, then this helped a lot because then the setups are all available, the space is there. I've noticed that other programs seem to be able to do this in the fall and the spring. I don't think we would have been able to do that. Just didn't really have the space or the number of lab setups that we needed unless we did it in the summer. The downside to that is I've had an awful hard time finding faculty to teach that in the summer. That's when they usually don't want to teach. So far I've succeeded, but I still don't know who's going to do it next year. Finally, this is something that I mentioned before. I've been very fortunate that the faculty has been very willing, but I feel like, again, they already have full-time jobs and they need to be compensated in some way. So maybe occasionally have teaching buyout for the faculties for a semester, use the tuition money to do that. So I think that's about everything I had to say. Maybe I'll stop there and ask for questions.
Thank you so much, Bob. Questions, comments for Bob?
Thank you very much. Thank you for being candid about your experience. I'm interested in knowing why it was set as self-funding, and you said the university was really kind of didn't want to have the same model like a regular master. So why it was really just self-funding, and even you cannot use that funding to help with faculty time buyout. I mean, the funding is self-funding program. I mean, why it was not set as a regular master like others? Kind of a combination between, like you pay as in master in computer science or master in physics. Okay, I'm gonna try again. The program was set as self-funded program. Why is that versus a regular master?
So the program is self-funded, as I say, and the question is, why is that? That was purely a local thing, that our administration told us that you can start a new program like this only if it is self-supporting. So in particular, even the in-state students have to pay this high tuition. This is just, I think, because of the budgetary constraints that the university finds itself under. I don't think it's a good model for the reasons that I have stated. It does have the advantage that eventually, when the total number of students ramps up, let's say to 20 or 25, then it'll not only be self-supporting, but we'll also have some money left over that we can devote to other things. We already devote some money to financial aid for women and underrepresented minority students.
Thanks. Okay, while Charles is setting up, we'll take one more question.
Thanks for the talk. Just have a question about timing. So if I think about a place like Intel or IBM, right? They want to get people that understand the physics, but also want people that know how to get things done in a research setting. And is there a reason to really sort of push it, limit it to 1 year and not have like a 2-year program where you have basically the first year of your program followed by a longer year of, you know, real research where you could sort of sink your teeth in and get into something?
Yeah, it's called IBM.
Answer the last question.
So Jason's question was about the idea of having a one-year program. 2 years has the advantage, and I think this is the reason that many places are doing 2 year program, is that if you really want to do a sort of serious research project, let's say with a thesis, then it really would take 2 years. And yeah, I think both have advantages. If a student is really just interested in getting into the job market quickly, getting some exposure to research, then I think our program is for them. If somebody really wants to do a serious master thesis, then I think 2 years is better. Particularly, you know, maybe in places which, you know, so UCLA and USC are doing master's programs, and there are lots of companies, startups around there where they can place students. It's a bit more difficult in Madison to have a serious internship program. We really only have one quantum startup in Madison. And so I think maybe for us, it's more appropriate to have 1 year.
Okay, please join me in thanking Bob. All right, and now I'm delighted to introduce Charles Robinson, who has over 30 years of experience in engineering and management in the public sector. In his current role as IBM Quantum Computing Public Sector Leader, he is responsible for preparing the defense community for the era of quantum computing. Charles also was instrumental in making sure that the IBM HBCU connections got made and the quantum computing program was launched, which is basically providing, IBM is providing $100 million to HBCUs over the next 10 years. So please, again, join me in giving a very warm welcome to Charles Robinson.
Good afternoon, everyone. Can you hear me? Awesome. Thanks for that introduction. My name is Charles Robinson, and I'm the IBM Quantum Public Sector Leader, as she mentioned. And I am here to talk about IBM Quantum Workforce Development, trends, what's working, what's not. IBM, as you guys know, is over 100 years old. And we've been able to make changes to how we do business over and over and over again. We've created markets in the past, huge markets. You guys probably know all of our technology, disk drives, barcodes, you name it, 1890 census. We've been around for a long time. So we know how to build markets. We know how to do business. We know how to actually help business accomplish their mission. And so right now we've been on a quantum journey. This journey started a very long time ago. I think back to 1926. And at that time, you guys are probably well aware, Heisenberg, as well as Schrödinger, they were writing 5 pages papers a year on these topics, wave mechanics. And I can't teach physics to physicists. So you guys understand how much progress has been made since that time. But where we are today, we are in a place where the world has shrunk and the planet is small. The internet, big data has increased the trajectory of information and has created an environment where the students in the back are consuming more information at such a fast rate that it is hard for all of the traditional structures to keep up with the advances. And because of that, IBM has tried to democratize quantum information and quantum technology. We've put it on the web. We've given folks access to the technology as we are developing it. We've actually made all of our educational artifacts open on the internet. And we're going to talk about some of that. I think it's important, though, to make a distinguishment between what IBM provides to students and what universities provide to students. One of the things that we are not doing is we are not giving folks a holistic view on quantum information science. That encompasses several modalities that I'm not going to cover today. I'm not going to cover quantum networking. I'm not going to cover quantum sensing. I'm only going to focus on quantum computing, which is an area that we have expertise, and that is a role that we play. So those things you guys have to do as university professors and stewards of our young people. And that is something that you do well and with the rigor that is absolutely necessary in a specific area like quantum information science. And so essentially, where are we today with quantum computing at IBM? So right now at IBM, we have over 360,000 registered users on 25 quantum computers. And that is unbelievable. And when you think about it, how many folks are using the publicly available quantum computers? It wasn't 20 years ago that folks could see a quantum computer in their wildest dreams. And so at the end of the day, when you got 360,000 registered users, it really teaches you a lot about how do you operationalize a research asset like this. And we're doing about 2 billion queries a day with quantum, and of course, this is the gate model, superconducting qubit platform. And that's just, it's phenomenal when you think about the volume of folks using the IBM quantum computer. Now, the one thing I can say is that our objective is to build quantum computers to help the research community perform exploration, scientific exploration. And right now, where we are with that is primarily in the realm of the small, right? We heard talks today from Oak Ridge National Laboratories. We heard talks over the last couple of days about some very unique material science properties and how quantum computing itself is helping understand that material science. And that's something that we're very keenly interested to make sure we continue with our partners. One of the things we heard yesterday from Senator Reid was that in order to teach the workforce of the future and to have a strong competitive quantum market, you need academia, you need industry, and you also need government. And so those are the kinds of partnerships that we're going to talk about today. And those partnerships is what we're trying to establish right here at this conference. And I want to send a shout out to Leonard Kahn. I see him over there, and also Vanita, and also Gaurav, because we've been working together now for about, 6 months now. And the goal has been to establish a comprehensive quantum partnership with industry, academia, and government. And it's not ironic that Senator Reid comes in and says exactly that. And so this is the IBM Stack. I'm sure you guys have seen this. This is the development roadmap. It's not often that companies publish in open source their roadmap. Usually, in order to get a roadmap from a company, you have to sign a non-disclosure. This was publicly put out by Jay Gambetta and the quantum team. And it is very, very clear it shows that by 2024 or so, we're going to try to get beyond 1 million qubits. And that's a phenomenal accomplishment. As a matter of fact, Jay Gambetta and Jerry Chow recently announced that they broke the millisecond coherence time breakthrough. And I think it was on a processor that was on Rev version 9. And when you think about that, if you look at all the processors that we have here, starting with Falcon, starting with Hummingbird, we're talking about 8 and 9 revs of these processors. So it just gives you some sense of the kind of process that's going on to develop the architectures here. And this is not experimental anymore. We're talking operationalizing, experimental platforms. And that's what the scale does to this. And so if you look at this, we started with circuits. We've actually developed a runtime environment. And the idea to develop a runtime environment is to make sure that you can do algorithms like the variational quantum eigensolver more efficiently. So when you do it over the cloud, over the web, it could actually do the feedback loop a lot faster. And so we needed a runtime environment. And so we've also developed a dynamic circuits capability. These capabilities are allowing the community, the quantum network community, to perform those circuits, those billions of circuits in a day. And so we are at a place now where we are developing libraries for folks to essentially call. So instead of you writing your own VQE or your own the JOSA algorithm or someone else writing a QAOA algorithm, we are making these algorithms available so you can just call them with Python code. And so it reduces the barrier of entry in a democratized way. And all of those things are available in our quantum network, as well as all of the software that we write. We put it at our qiskit.org site, and I'm sure you guys are all aware of that. And lastly, what I will say about this slide here is that right now we're focused on model services. So we're moving up the stack. Right now, if you look at the processor stack, we already have went from circuits to programs to models, and right now we're in the process of creating an engagement model, right, focused on natural sciences, optimization, machine learning, and finance. And we have a partnership model, and I'll talk about this a little bit later, called the accelerated discovery model, that we are combining hybrid cloud. Also, we're combining high performance computing as well as quantum computing in an offering that we'll discuss a little later. And we're on track. So for those of you who haven't seen this, essentially we call our quantum machines by city names. And so right now, we're on Montreal, which has 128 quantum volume. We just decommissioned Manhattan and just stood up Brooklyn. Brooklyn's in the house. And essentially, the team has been working very, very hard to stand these systems up, make them operational. And we'll talk a little later about how we've deployed them on-prem. And before we get there, I just want to ask everyone to turn around. Chris, can you raise your hand? So that's Chris Larakis. He is actually responsible to deploy our quantum computers, and he's actually deployed them in Germany. He has deployment underway for Japan, and of course, Fraunhofer. We'll talk about We'll talk about the Cleveland Clinic last. Next slide. Has anybody ever seen this picture? Raise hand. Does anybody know what this picture is of? All right, good. So we have one person. This is a picture from 1946. It is at Lincoln University, and you guys know the guy up front, but you probably don't know any of those folks in the audience. The guy up front, how do you think he feels right now talking to an audience of all African-American physicists? That's exactly how I feel right now. So, but what I can tell you is this, is that Einstein had a personal relationship with the president of Lincoln University, and that is his office. His name is Horace Bond. Horace Bond was the first African-American president of Lincoln University, and that was 1946. Lincoln University has been around since 1860 something, and he was the first African-American president. But because Horace Bond and Einstein had a great relationship, Einstein was actually, at this time, his health wasn't that good. But he had to meet Horace Bond because Horace Bond was a champion of STEM. He was a staunch civil rights leader. As a matter of fact, his son, you may know him, his son's name is Julian Bond. And so at the end of the day, I asked one of my colleagues who went to Lincoln University and asked them what they talked about. Of course, they talked about particle physics, relativity, all of the things you guys discussed today, complexity theory. And, you know, for those in the room who don't know this, there's a rich history in the HBCU community going way back of folks that actually do quite a bit of physics. You know, and I think one of the ways to tap into a diverse and inclusive environment is actually to put the work in and go out and get them, find them, talk to them. That's what Einstein did. Anyway, let's just go to the next chart. What do you see here? I see 3 sets of eyes. Can you all see the 3 sets of eyes? Okay, so look at the young man to the right. Look at that intensity in his eyes. This is why we cannot fail to teach our young people what this quantum information science era is all about. I mean, that is passion supreme. Look at that. And to be honest with you, this is why we are privileged to be in this position in the early stages of this quantum, well, some would call it the second stage of the quantum generation, revolution. But we're in a privileged position right now, all of us here in this room, because of these eyes, that intensity. I was teaching K12 kids quantum information science. Now, how do you train K12 kids quantum information science? Like Einstein, I'm the black guy, and I'm talking to these young people, right? And this audience was a tougher audience than you guys. This gentleman right here in the blue shirt, how do you explain quantum information science to a young kid like that? Well, you do it the way that most people do things, and you explain it what it is and what it's not, and you compare and you contrast, and that's what I did. I showed them and I made the example of what classical computing was. I asked them what was inside of their iPhone. It was like a chip. I said, well, here's what a chip is. I said, what does your iPhone actually do? Well, it processes. We provide input. We get output. I said, that's in general what a von Neumann architecture is. has memory, right? And they got that. They didn't necessarily need to know every detail about what a classical computer was to be able to understand how to use it. They got the fact that a classical computer, along with a transmitter for a phone and a receiver, would allow you to do something useful. And so what I tried to do was relate that to quantum computing. And so I had to describe for them, oh, by the way, I had a bunch of stickers and a bunch of things that excited them. And I was very animated. And I captured their attention. And what I'm not seeing here, what you're not seeing here is 1,200 students at this STEM Expo at Morgan State University. And I had 11 minutes to make an impact with these young kids. And it was around this size all day long, right? Now you can do more harm than good in that circumstance. But my point is unless we start to increase our velocity and trajectory, we're not going to win the battle of trying to educate the next generation workforce in quantum information science. And so this was a very unique experience for me, and it was very rewarding. So what they're seeing on the desk here is mainframe chips, right? And I said, okay, since you guys know what a processor is for a phone, let me explain to you what these processors are. I said, these processors are in refrigerator size classical machines. They didn't need to know what the difference between a mainframe was and all they needed to know was the refrigerator size, right? And I showed them that. And then the other thing I told them was that these machines that are refrigerator size are on the back end of what your cell phone connects to when you talk to the internet. Simple concepts. They got that. And then I tried to explain to them what a quantum computer was and how it worked. I explained to them what a qubit was based on what a bit is. They understood what bits were. I tried to explain to them what the probabilistic model was, entanglement, as well as superposition. Now, how do you do that with a kid this age? How do you explain entanglement and superposition? Well, if you take the IBM ambassadors class, and we're going to talk about that in a second, the way that they teach us superposition and they teach us entanglement is the coin toss experiment. And so I literally had 2 coins and I did the physical coin toss experiment in front of the kids and talked about whether the 2 coins at the top of the height of the spin, what were they? Was it heads or tails? Let's just say if this quarter and that quarter was entangled, it would be heads and it would be heads, or it would be tails and it would be tails. And they got it physically, just a coin toss experiment. And what superposition was. And the kids got it. And at the end of the day, I think we sell our children and our students short about how much they can grasp, right? So here's a refrigerator-sized machine. Now you guys have seen from Oak Ridge all of the great things that they're doing. And I don't necessarily need to recap the relationship that Oak Ridge has to the community writ large in quantum, but suffice it to say that this is one of our strong partners. And when I talk about government, academia, and industry partnering together, this is the kind of partnership that we're talking about. They're one of the centers, the national centers, as they mentioned in the talk, Travis. And right now, this is their refrigerator-sized machine, which is classical. But we all know that this refrigerator-sized machine with all of the NVIDIA cores that's doing machine learning and all of the huge file storage space can't solve some problems. And that's why we're here, because some of those problems, particularly at the very small scale in physics, can't be solved with high performance computing, whether it's computational fluid dynamics or finite element analysis. We just can't get there from here. And so that's why quantum has so much promise. And we all understand that. But what we are really talking about today is how do we prepare our workforce for the future? And so, you know, when I talked to Leonard about this, he was adamant. He was like, Charles, we're going to create a master's program. It's going to be a bachelor's and master's program together, which I thought was unique. And it's going to be a single master's program. I said, well, that's awesome. That's awesome, Leonard. And, you know, then he said, okay, it's going to be like prerequisites that you have to have. Well, I was like, well, wait a minute. What about the people who, you know, they graduated years ago, you know, they just needed a certificate program or some sort of program that they could take to retool and reskill. And Leonard said, well, can you help us with that? I said, absolutely. So the kind of partnership we have, Leonard is looking at the IBM Skills Academy, and that will help him jumpstart the students who have graduated. It'll help them create his own certificate program. It is something that we have within our own program. We've created our own certificate program, but we empower our partners to do the same. And Leonard's taking advantage of that. And I was looking at this slide, right? And I was like, okay, I would take this. It's 38 credits. It looks like it's a year, right? 2 years, right? 2 years. And the reason why I would take it is because of the quantum computing internship program. Because most kids, they're going to want an opportunity to get a job. Not only to go into research, as you mentioned, but they're going to want to go to work at some point. If you're a parent, I think you understand what I'm talking about, right? And so when you're at the high school level and the college level, you got to definitely make sure that the program is hands-on. And I'm not just talking about from a programmatic standpoint with QIS, but I'm talking about from a physical hands-on perspective, right? I think one of the person that was from Pittsburgh said that there was a Schrodinger's occasion or Hamiltonian that could never be zero. He could never see that state. So it was a picture that he had with a 1 and a 0 at the same time, and you really couldn't touch it. Well, we built one. There it is. It's a 1 and a 0 in the same time. You know what I mean? So it's on the table. But yes, I get the point that a Hamiltonian is 0, but the kids don't really even understand what a Hamiltonian is at this point. So you got to show them a 1 and a 0 at the same time. You know what I mean? And you got to tell them that you know Raspberry Pi, so you can actually use your Raspberry Pi, put a QIS component on it, and run quantum computer from something that you can build right now. So they can actually have physical buy-in to how they can operate a quantum computer. And that's what we've shown them. And this demonstration was given by one of our quantum ambassadors, Hasi Norland, and 3 of those young people had projects in Raspberry Pi. And so that project was to implement the edge device, not a laptop, to do quantum programming. And so that's an undergraduate way to get folks engaged that are learning the process right now in STEM. And the reason why I put that up there is because Hasi Norland, he's just a phenomenal guy. And for him to do that on a Raspberry Pi really opened up some possibilities for the students to see. So QIS. So today, QIS, everyone knows what it is. It runs on the Microsoft platform. It runs on the Honeywell platform. It runs the Honeywell platform. It runs the IBM backend. Of course, we have democratized QIS. If you go to QISKit.org, there's a lot of code out there. The community can actually use it. I'm sure some of your students are already using it. And I'm sure you guys are all familiar with this, so I'm not going to spend a long time with this. But we have an online textbook, which is interactive. And so if you go out to the book, you can go to an algorithm, let's say QAOA, click it, run it right there. It is phenomenal. And it is being created by a community of folks. That's the important thing. It's not just the IBM team that is working on what this is, it's a community of contributors to this, which is very important to open source, to reduce the barrier of costs for knowledge in order for folks to have access. And I heard that cost was sometimes an impediment, although I believe it's more than just cost to having access, but access is important. That's the point. Now this, we talked about earlier, which is the specific quantum system for the textbook. This is an example of a specific algorithm that you could actually call in line and when you create your quantum circuit. And so this is something that we are doing to reduce the barrier to programmers so they can just use inline code. Everybody's programming in Python at this point, and they can actually run programs. And today I'm going to ask Robert to stand up or raise his hand. So Robert runs our Quantum Ambassadors program, and Robert wrote a book, and that book is incenting me to be able to take this book to go out and teach high school students on how to program in Python. And another one of our partners, Bob Suter, has wrote a couple of books as well. And I use those books specifically to teach high school students, college students. I leverage it significantly because it helps them get a deeper understanding of how to program on our platform. And this is Robert Laredo's book here, Python. And Hasi Norland, as I mentioned to you guys earlier, that's his book as well. And so we provide a lot of opportunities for people to learn quantum computing. These are just a few, right? Robert Laredo, Hasi Norland. I want to talk a little bit about workforce development and a survey that was done through the Quantum Economic Development Consortium. Shout out to those who are in the Quantum Economic Development Consortium, Celia Messenbacher and the team. There was a survey that was done, and these are pretty much the questions that was posed to industry. And those questions were, what are you going to do? How do you expect and who are you going to hire in the next 3 to 5 years? And for what jobs and skills are you looking for? Very simple questions. And for what each job, which degree do you require? And I looked at this list and I thought to myself, wow, experimental physicists is really a large number of what the commercial industry is looking for. But as I started to look at this closely, essentially most of the STEM disciplines are in demand. And so what I see from this is that universities like URI, University of Wisconsin, and Pittsburgh is doing a tremendous job, period, even now, right? So I think there's kind of a misnomer that there's a skills gap, because a lot of times that when you go to a company, they're going to retrain you. I see that the CEO is Zapata in the back, and I know that he trains folks who comes through his doors with STEM skills on what Zapata does specifically, and that's important. But the other key to this is, when young people come to your school and you have to advise them, I think it's important, and I think the gentleman from Wisconsin mentioned this, that you have to essentially make sure that you have them understand what the market value is for the decisions that they're making while they're in school. So it's important for you to keep up with this, to understand what the companies are saying. And QEDC is a good place to get that information. And so the other thing I learned about that study was that there's plenty of opportunities in the bachelor's and master's program space. And so I told Leonard that that sweet spot was really a good place to start. And that's where he started. Have you guys ever met an error correction scientist, PhD in error correction? 20% of them, most of them are PhD. We have a few of them at IBM. They teach our quantum ambassadors class. They're kind of a different set of folks. They look at quantum error and error mitigation, which is, it's not the most complicated thing in the world, but it's not the simplest either. To be frank with you, there's a lot of need for that now. Will it always be that way? It is now. But there's a lot of other positions that are in demand. Let me see if mine is on the list there. My position. Technical sales and marketing, there I am. You only need a bachelor's degree primarily for that. So I think I'm okay. All right, so why are companies anticipating, a broad range of jobs and skills? Well, I can tell you why at IBM. We're moving from an environment where we're developing the fundamental research and we're working out the system, and now we're operationalizing the systems. We're developing data centers to put them in with new IP. And we're moving to a place where this becomes a traditional business unit, and we need all kinds of people. It's just that simple. Where a lot of times, folks in our community, they're still looking at, whether it's Betamax or whether it's VHS or whether, and we're way beyond that. You understand what I'm saying? And so, and that's just real, right? But this is our team in our workforce development training. And if you notice, you see Heather. Heather, can you raise your hand? Heather Cortez helped organize the conference with me and Leonard, and I wanted to tell her that I really appreciate her efforts. Heather is in ops, in sales operations. We all went to quantum computing training, and that's the point, right? We all went to quantum computing training, and it was all diverse, right? So, and it's not just one level of quantum ambassadors training. It's several levels, and Robert's responsible for that, right? And so, at the end of the day, companies will retrain the students that you train. You have to keep that in mind. Right now, it's about trajectory to get the program in place, or you will lose them because there's so much information out there online, and these young people learn more online than you believe. The trajectory is moving fast, so I'd implore universities to make sure that they move out on getting this in place, as URI has done. In any case, this is our quantum ambassador class, and we're doing, how many of these are we doing, Robert? 10 to 12 per year. And so this is the way that IBM does folks that are in the field upskilling, right, for our own company. But we also have companies working in this space in the K12 range. The next speaker, right, Qubit by Qubit, we've worked the program with them so that they can do K-12. And I'm not going to steal her thunder. I'm going to let her talk about what they do. So we have partnerships with folks out there who do this and do it quite well. And so at the end of the day, I just, what I would like to see from this is a real faster trajectory, I guess is how I would describe it. And so in terms of partnerships, right, when we partner with folks, we tell folks like University of Rhode Island, we have a certificate program. If you want to do that, this is how you can do it. And so we make it easy. So when Leonard and I started, he told me how long it takes to go through the curriculum process. It takes over a year. And how long it takes things to get done. I said, well, just use ours. Here's a way that we could just give that, just show you. He had a relationship with IBM in the past, so he understood what it was. And so that way he can start teaching his former students that graduated from URI and giving them certificates in a very, in a shortened time frame. Everyone knows about the courses at MIT, the 4 courses you can take. It's quite, quite good. But when you're starting from scratch, where do you start? And so that's what partnership is all about. And so we have an associate certified developer program as well. So as far as the HBCU community and diversity and inclusion, so we embarked on, as a part of democratizing quantum information science or quantum computing, we looked at the educational market globally. And so one of the things we looked at was, how do we raise the boat for everyone? So essentially we looked at Europe, Africa, Asia, United States. And in the United States, we decided that we would establish the IBM HBCU program. And right now, that program is being led by Kayla Lee and Benita Zazueta. And we have 23 HBCUs as a part of it. And of course, Thomas Searles, who's a PhD from Howard University, is leading it. He's a terahertz physics researcher at used to be at Howard. He just recently moved over to the University of Chicago. And for some of you guys have worked with him in the past. And so, but we have a lot of HBCU organizations as a part of this. They have a quantum hub. Howard runs that quantum hub. Each of those HBCUs that are part of that quantum hub, which they're listed here, they get free quantum computer training, as well as they have access for certain researchers to get quantum research dollars from the IBM quantum program. And we also have convened a board of HBCU people to help IBM coordinate the program. That way, there's a relationship with IBM quantum leadership and the HBCU community. And so those are kind of the components. We've also paid for 5 of these universities to join the Quantum Economic Development Consortium. And all of them are in the Workforce Development TAC, which I'm the vice chair of. And so that gives them an opportunity to join this space. And so, and this is not the last time that IBM is going to work with a specific demographic from a diversity and inclusion perspective. This specific demographic, we chose all of the ABET accredited schools. It's like 15 schools that are ABET accredited. They represent 4% or 30% of all of the Black graduates in engineering in the country. And so we were very selective and targeted on what we were going to do here. And this is not the last time that IBM is going to work with a diversity and inclusion community. This is the first one that we're looking at, but we already have plans for another, and I can't announce what that is at this time. Some of the stakeholders that I'm working with is in this room, but we're going to do more when it comes to diversity and inclusion in the quantum space. We all need to do more. It's not too hard, as I heard. It's not about money. As Einstein proved when he visited Lincoln University in ill health to a friend and taught quantum computing in '46, it's about desire and will to do. So these are our quantum partners. So these are all of the people who we partner with, and there's various levels that we partner on. And so if you look to the companies all the way to the right, if you see those companies there, those are all the academic partners. And so we believe strongly that IBM's relationship, particularly in quantum information science, has to be a partnership between industry, academia, and government. That's the way you win. And if you look to the left, those are the larger splash partnerships that you've seen. Accenture, ExxonMobil, those are the businesses out there that are looking for business advantage and putting a stake in the ground with quantum information science, right? And so But this is a huge list. It's over 170, 12 industry, 20 hubs. So for those of you who don't know what the business model of a hub is, it is a logical connection, a logical construct where a hub owner, let's say Howard, will have a bunch of hub members, let's say all of those other 20 HBCUs. Now, traditionally, a hub owner, they could actually resell their access. But most of them do it based on general interest and partnership with their partners. And so, as an example, Leonard, as a hub owner, can use that hub to have every one of the small businesses around this ecosystem or any other student small business that want to start in that space use that hub. It is a way to create community. And that's what this is all about. And so if you look at the member list, which is right next to the hub list starts with Brookhaven National Lab, and the member list starts with A star. So those are all of the member lists, and those are all of the hubs. Second column, third column. The fourth column is all of our quantum startups. So we have a quantum startup program where we're working with a bunch of different IP producers in the quantum space, and we provide them specialized access, specialized relationships. An example of that would be the CEO of Zapata, right? He has a research project going on with IBM, and that research project is helping IBM, as well as it is providing him with access so it can extend his capability. And that's the kind of partnership that we have with our startups. And we have a bunch of them. And they just so happen to be in the sensing space, networking space, point in time space, position navigation and timing space. And we go to market with them as well. That's a key differentiator in our partnership program. And we have invested in some. And so this is really a powerful statement when you have a quantum network and you have such symbiotic relationship between your partners. It's the kind of ecosystem you want to build even at the university level. And so, as I mentioned, I'm not going to harp on this. This is something where I show that we do a lot of business with the academic community, and that's why we're here. We have an emerging market, and we're trying to partner on every level that we can, right? And here's the government research. So I am from the national security community. I talk a lot, but I don't say much. That's what I tell people. But one of the things I do tell folks about what the DoD and the national security community is doing is that they are very concerned about the QIS market and where we are from a national security perspective. And that's why I'm imploring all the folks in this room and those who are looking online that we increase the rate. And I know you guys are thinking that we're moving out at a very fast rate, and we are, but we need to increase the rate of how many folks we bring into this community. That's what I'm saying. And it's a global community. The global community is one that IBM has been working on for some time. I think I mentioned KO University and the system that we have deployed out there. I didn't talk too much about the business side of this, but there's a huge business side of this as well. JP Morgan, huge financial component to this, and IBM has a huge history in the financial sector, as you guys know. But this is the point that I wanted to make here that I thought was important. As we move up the stack from a quantum roadmap perspective, as we go to a runtime environment, one of the things that I want to make sure of is that you guys understand that we have a new program called the Accelerator Program, and that program is based on scientific discovery. It's the scientific method, and the scientific method will incent us to to try things in a faster way, to hypothesize and move through the cycle in a much faster way, to be able to in a sense, create faster loops and readiness assessments so we can have joint use case application development. And we do that with the scientific method by leveraging three capabilities: hybrid cloud, AI, and quantum. And so I know I'm getting some attention here, so I don't have a whole lot of time to talk about this, but what it helps us do is it helps us get closer to simulating quantum systems, as well as bringing artificial intelligence to bear on some of these scientific use cases. And also, it is a new concept that we have bridged with the Cleveland Clinic to help the Cleveland Clinic accelerate discovery in healthcare and life sciences. And so we had on Sunday Anthony Annunziata, who is the lead for the accelerator program at IBM. And we believe that this new type of relationship that we're building for our partnerships with all of our quantum network, as well as those who want to specifically join a quantum accelerator partnership with IBM, is going to be able to incent research a lot faster, to increase the trajectory of how fast we do research. An example would be, we have solvers in AI that can actually comb the web using natural language processing, that can scour every research topic in your particular field and present to you as an example all of the papers associated with your specific research field, where you don't necessarily have to go do that. It'll actually go through the actual papers themselves, the actual language, as well as the equations, and it will present you with a pool of research that is specific to the things that you want, based on artificial intelligence, natural language processing. And that will help you as an individual researcher figure out quicker how to get to the places that you need to get from a cognitive perspective as you go learn what you need to learn to do your job. And so those are the things that we're bringing to bear on an enterprise scale to help to increase the OODA loop, if you will, of the actual research in the scientific method. And we believe that that will enable better research from the researchers out here in the audience, as well as a faster rate of discovery for the things that you guys create through research that provide innovative things to our society. And so with this accelerator program, we encourage you guys to explore that. And that is a partnership model that I believe that is going to take us into the, it's going to help us accelerate the second quantum wave that we're in. And here's some examples of work that we've done. One is with UK. I have 2 minutes. So I'm going to pause here and just say that here's another example that we're working with India as well. I'm going to pause here. I noticed I didn't get the 2 fingers when I put the Indian slide up, but I'm going to pause here and say, are there any questions?
Let's thank Charles. Thank you so much, Charles, for that wonderful presentation. While Kiera is actually setting up, Charles can take a couple of very quick questions. Anybody?
So one thing you kept mentioning over and over again is trying to make sure educating younger people and making sure you can fuel future interest for the next generation when it comes to quantum computing. Is there any suggestions that you may have for high school or middle schoolers or even new college students in that range for places you can go to explore an interest in a wide variety of different places for quantum computing?
Yes, as a matter of fact, the young woman that's coming up on the stage right now,
Oh, perfect.
her company is called Qubit by Qubit, and she was funded by IBM to develop a program for the workforce for K through 12 and young folks. So she is going to explain all of that to you at this very second. High five.
All right, then let's thank Charles again for that wonderful presentation. Thank you, Charles. All right, so now I'm delighted to actually present Kiera Peltz, who's the founder of Qubit by Qubit, that focuses on training the next generation of students for quantum information science related jobs. Qubit by Qubit is the online learning initiative of the coding school that you might be familiar with. And that is a nonprofit that aims to empower the next generation through computer science education. Qubit by Qubit has partnered with a number of organizations, and Kiera is going to talk about what Qubit by Qubit is doing in the quantum arena. So please join me in welcoming Kiera.
Hi, everyone. Thank you so much. My name's Kiera Peltz. I'm Executive Director of Qubit by Qubit. As Charles mentioned and kind of implored us all to accelerate the development of the workforce, well, I'm here to say that we're ready and equipped to do so. We have trained over 15,000 students ranging from elementary and middle school students all the way up through members of the workforce. And today I'm going to talk a little bit about some of the things that we've learned, as well as the challenges that I see the space of quantum education and workforce development facing. These are also some of our incredible students. Most people think they're stock images, but well, so we really come from a social mission for Qubit by Qubit. We believe that it's important not to be focusing necessarily on the technologies of today, but looking at what technologies are going to be prominent in the next 5, 10, 15 years, and making sure that we're training students accordingly for those skills for when they enter the workforce. So we kind of have 3 main pillars that we're focused on: early access to quantum education, increasing diversity in quantum, as well as training the next generation of quantum leaders. I will say what we're not just solely focused on making sure that every individual who goes through our program goes into the quantum industry. We implore our students to see all of the applications that quantum will have. We know that there has to be creators and developers of quantum computers, but there also has to be adopters and those who are going to become business leaders and advocate within, their own industries. And so we really take a broad approach, making sure that we're creating inclusive programs that bring everyone in, not just those that are necessarily the most STEM inclined. Our advisory board, many of the members are also speaking. So if you're on this call, hello. No, we started off as a K through 12 organization. My background is in computer science education for K through 12. But what we found out when we piloted some of our initial programs for high school students is that there was so much overwhelming interest from university students and members of the workforce for programming. So we've really responded to that need and gaps within the system of providing supportive programming that creates a pipeline for students from an early age and can continue carrying them on through university, or for current workforce members, allowing them to enter the quantum space. So we have a number of different program options and opportunities. Again, we're always coming up with new ideas based directly on feedback from students. So we do surveys, focus groups, one-on-one interviews with our students, or a collection of them before and after all of our programs, to make sure that we're meeting their needs. So our reach, as I mentioned, in the last 2 years, we've taught over 15,000 students. We've taught students from 125 countries, 50 US states, and diversity really is front and center to everything that we do. We believe that we don't want to make the same mistake as the classical computing revolution and try to address diversity later on. We want to try to make this as inclusive as possible from the beginning. So 55% of our students are from traditionally underrepresented backgrounds in STEM. And just one of my favorite quotes from one of our 12th graders from North Carolina who completed one of our 2-semester courses. He said, "I began 2020 wanting to be an electrical engineer. By 2021, I knew for a fact I wanted to be a quantum engineer. That would not have happened without this course." I could show you hundreds, if not thousands, of similar quotes like that, which just to me underscores the importance of providing quantum education at an early age. Students are well equipped to take on these difficult, complex topics. I'll talk a little bit more about this later. So just in terms of some of our outcomes and what we found. So we actually found that across actually all of kind of the educational levels of our students, but particularly for high school and university students, those who took our quantum computing class were far more likely to say that they were going to take another STEM class, or more likely after they completed one of our programs than before. They were also a lot more likely to take a more advanced STEM class than they were before our program, and their confidence was significantly increased. One of the most interesting findings that we've had is we looked at confidence between the genders, so males and females, for our courses before they started. And we saw that there was about a 15% difference in confidence in STEM. By the time students had finished our course, we had halved that to 7% of a difference in confidence. So I think I have my theories, and so does my team, about why quantum is actually such a great introductory course for a lot of students to increase their confidence. I will talk about it a little bit later, but you know, the interdisciplinary nature and the fact that there's so much left unknown, it's one of the first times a lot of students have ever heard, wait, we don't have all the answers. There are really incredible, brilliant individuals working in this space and they can't solve these problems. It's a relief for students and it makes them feel like they can do this too. So a huge part of our program is humanizing the field and making students see that everyone can participate in this space. Yeah, as some of these other statistics suggest, our programs and just access to quantum education significantly increases students' interests across educational levels in pursuing further quantum studies or even pursuing a career in quantum. Just a few things about what our students are saying. You know, I won't read these quotes, but students have talked about at the high school level how this has completely changed what they want to do in college. Over, I believe it's 88% of our high school students report that they have a clearer idea of what they want to study in college after completing one of our programs. Again, I attribute this largely to the interdisciplinary nature. We have a lot of students who say they want to go into quantum. But we also have a lot of students who say, you know what, quantum's not for me, but now I love programming. I never was exposed to programming before, and I was in this course, and that's what I want to do later on. We also, you know, because of our global reach, really try to make sure and because a lot of our programming is virtual, we're able to reach students that, you know, don't even have a lot of opportunities to participate in STEM programming, let alone quantum programming. I would just like to highlight the third quote on here. You know, we weren't expecting when we first launched a course that included members of the workforce. we made it very clear that they wouldn't be able to get a job after completing an introductory 8-month course that had limited prerequisites. But anecdotally, we found that a number of members of our workforce actually did change companies. I met with a member of our workforce a few days, or one of our students from the workforce a few days ago, who said that he actually pitched the CEO of his company a plan for quantum adoption over the next 10 years. And when his CEO said, you know, we like this, but it's just not a priority in the near future, he actually left the company and was looking for other work. So again, I think there's a lot of opportunity and a lot of people that are hungry for this and willing to invest in it. So I'm just going to spend a few minutes to talk about kind of our program design. So in fall 2020, we decided to launch our first ever 2-semester Introductory to Quantum Computing course for what we thought would only be high school students. We were excited about this. This was the first 2-semester course really offered and available. We thought we would have 1,500 students in it. We're accredited by WASC, which means that actually high school students can receive course credit if their school approves it. So we were really excited that students wouldn't have to take this as an extracurricular, but actually could take it and it could be on their transcript. What we found, though, is there was so much interest from university and members of the workforce that we ended up opening up the class. And so we went up to 3,000 students, we went up to 5,000, we went up to 7,500. We capped it at 7,500 students. We had a wait list of almost 10,000 additional students waiting to take the course last year. So I'll just spend a few minutes and well, before I go on, this was all thanks to IBM Quantum, who completely funded the course last year and this year as well. But I just want to spend a few minutes kind of talking about how we designed this course and what are the components, so you get a little bit of a better idea. So the course was 8 months long. All live instruction, which I think is, you know, one of the things that separates us from a MOOC and why we had such a high completion rate, even though there was a lot of kind of responsibility here. It was all virtual. So again, students from anywhere in the world could participate. We had students from 125 countries participating. We had limited prerequisites. This was really important to us. We did not require any prior programming knowledge, any prior physics knowledge. We just asked that students have completed a geometry class, which many students complete in the first few years of high school. And we did have grades for the course because a lot of students were taking it for course credit, but it was pass-fail. A huge part of our program is making sure students feel like they can fail. We survey students and ask them sometimes, how well did you understand this topic? And for those that score or say the highest amount, we say you probably didn't actually understand it then. Our weekly components, last year we had a 2-hour lecture. We shortened it this year to a 1.5-hour lecture. It's every Sunday. We don't take attendance at the lecture. So if students can't attend, they can watch it later. We also have a 1-hour lab with a TA who are typically PhD students in quantum, but we have some master's and undergrad students as well. This is a highlight for all of our students. It's a chance for them to do more hands-on learning. It's a way for them to engage with their fellow students. They highlight their TA as one of the highlights of the program. And furthermore, because of the near peer model, particularly for high school students and undergrads, we have found it really beneficial for them to have relatable role models and to help them make those difficult decisions of, you know, where do I want to go to college? What do I want to study in? What do I want to study? Where do I want to do graduate school? This is also the first time a lot of our students have ever interacted with someone that is going into a field like quantum. So being able to, again, I'll say it a second time, humanize the space has been really critical. We also have optional weekly components. So we recognize the course is large. In the lectures, we answer as many questions as possible, but there's not a, we can't get to all of them. So we do have individualized support options. We have weekly office hours that students can drop into. We have a homework review session where we go over 50% of the homework before even submission. So students still have to be able to work at the additional problems, but at least helps them if they're stuck. And then we also have an online resource called Piazza where students can ask questions and our TAs or other students can answer them. And as I mentioned, we're accredited. So we're partnered with over 100 high schools around the US, where for the first time, quantum computing is widely accessible and available to schools for course credit, which, again, for students from low socioeconomic backgrounds who have a lot of responsibilities after school hours, this is critical to making sure that our programs are inclusive. And we're excited to continue to expand and partner with more schools going forward. Just a little bit on, and everyone asks me, well, what did you cover? We have changed kind of the ordering based on the course last year, and we also did the course again this summer. But just so you get kind of a general awareness, as I said, there's limited prerequisites. So we cover all of the math that's needed. So vectors, matrices, multiplication. We cover the programming. So we go through Python programming. We introduce them to Qiskit. They learn by the end to program a 2-qubit circuit, as well as to mathematically predict the output. We also go into quantum algorithms and protocols. Because of students, many students limited Python knowledge, we don't have them completely program the algorithms or protocols, but our goal is for them to really be able to understand what's happening and be able to plug in certain sections. So we go through Grover's, we go through VQE, we go through QKD, and if time permits, a few others as well. This is just a small thing, but something I thought was really cool in our course in 2020 through 2021 that was open to really everyone. We actually had a lot of families taking the course. It usually would start off with the high school student taking it, and then their sibling would start to sit in on the lectures, and then the parents would start to come in, and they would finally say, well, we're all doing this, we're all doing the homework, I might as well enroll in the course ourselves. So one of my favorite quotes is actually the middle one by the Thurston family from Utah. They said that through the Qubit by Qubit course, our family was introduced to a new world we'd always wondered about, but seemed out of reach. It's a common theme, out of reach, that we hear. At school, 13-year-old Abigail realized she finally understood Schrodinger's cat jokes. At his programming job, Dylan stumbled upon quantum key distribution and big O notation. Spooky action at a distance has popped up in books Jessamine is reading. Seamus's entire math class this year was introduced to him in 1 month of quantum lectures. And since then, his trigonometry class has become one of his easiest. I think this quote just really illuminates and highlights that there's something for everyone to learn in quantum and to relate to their own lives. So kind of taking a step back, most of our programs are designed in the same way, whether they're a camp or a summer school or a 8-month course, in terms of, kind of combining this scalable model with individualized support. So I'm just going to go through a little bit about what we actually have learned from teaching 15,000 students quantum computing in the last few years. And I'll say it's a lot, so I'm happy to talk more about it afterwards. There's just a few of, I think, the big things I get questions on all the time. So there's significant interest in learning, quantum and QIS more broadly. Second, K through 12 students are really well equipped to learn quantum. We actually piloted a 1-week middle school course or camp this summer. It was met 3 hours a day. It was virtual. And every day my inbox, I get at least one message from a parent or student asking when we're going to have a longer course available for them. They were really able to pick up these complex subjects incredibly easily. Third, I mentioned this earlier, but learning quantum really increases students' interests in other STEM fields. So I hear a lot of people, they say, well, is this a course that only, or is quantum something only students who take a lot of AP STEM courses can do? And I say, actually quite the opposite. I think it should be before many students take other STEM subjects, because the interdisciplinary nature and the fact that they're seeing something applied really strengthens their interests in other areas and kind of creates the perfect pathway for further STEM exploration. Or if we're going to ensure the quantum workforce is inclusive, diverse, and equitable, we have to start early. I am approached a decent amount about, how can we get workforce members trained immediately? And I think the workforce is well equipped to, start being upskilled or reskilled. But we're not going to increase the talent pool, and we're also not going to increase the diversity of the space if we don't invest in university and K-12 pipelines. And then last but not least, there are gaps and continue to be gaps, even with the educational initiatives that are coming out that need to be addressed to kind of create this seamless pipeline for students, and so they don't fall off. One thing from our courses and our programs, we're working on a more advanced course, but we've really focused on providing introductory kind of courses equivalent to first semester of a college level quantum course. But students ask us all the time, like, what's next? What can I do? Either their university doesn't offer further programs, they're a member of the workforce and it's too expensive or still too advanced, or they're in high school, and so the options are limited. And then just the last thing that we've learned, inclusion matters. It's not just enough to say it matters, but every single aspect of one's program needs to emphasize this. So from the marketing material to even how students fill out the application. We have a lot of students who say, I wouldn't have applied for this course if you didn't have an emphasis on diversity, because I didn't want to repeat other STEM experiences that I've had. We also, it's really important to have inclusive program design. So one thing that we found out last year is we had about 800 students from developing countries taking the course on their cell phones. We were not prepared to make a mobile friendly course. And so we had to quickly kind of iterate and make sure that we were able to do that. I will note that a lot of quantum platforms are not mobile friendly, and it continues to remain a barrier. So it's all these different aspects that we have to be thinking about as we're creating programming. And then just last but not least, a few challenges that we see in the space. And again, similar to the lessons learned, I could spend much longer on these. So happy to talk about it later. But just one in general, in terms of outreach, there's still limited awareness of quantum in K-12 amongst students, amongst educators, amongst administrators. We have a full-time team dedicated solely to outreach, and it just takes time and effort. It's not impossible, but it takes a lot more time and investment and funding than a lot of people would like or think is necessary. There's also, for people who do know what quantum is, this belief that it's only for geniuses. And so being able to change that and pull that back is really critical. And then just, again, reaching underserved communities. Again, we have to put in the work. It takes time, but we can do it. It just is going to require significant investment to make sure underserved communities are not left behind. I will say, just anecdotally from our experience, when we email out schools offering our programs and our courses, even for free, Private schools and charter schools in more affluent neighborhoods are the first ones to respond and take advantage of this opportunity. Teachers in underserved communities, they are strapped, they are overworked and overburdened. So how do we make it as easy as possible to get students from those communities, to get teachers and administrators from those communities engaged? That's something we're continuing to work on and think about, but is going to be critical going forward. Second, curriculum design. So I've heard this in a few presentations so far, but meeting students where they're at is really difficult because they're at a lot of different levels. So, you know, even in our introductory course, we have some students who have been learning Python for 5 years and they're much further along, or they've taken calculus or linear algebra already, and they're much further along than someone that's just finished geometry. Obviously, there's limited bandwidth and resources that we have at our disposal. So how do we make sure, at least for now, that we're creating programming that can kind of meet students at those levels? One thing that we do is in our lab sections, we have a beginner, intermediate, and advanced that students select into based on their STEM skills, and we accelerate the labs accordingly and make things more challenging. But I think eventually what I would like to see is separate programs where we can have a program for students who have already studied computer science and say, okay, we don't need to teach you the basics of Python. We can move much faster, and then have another program for students who have no Python knowledge and say, that's okay. Like we'll hold your hand and walk you through this. And then just the last one, getting funding for continuous programs is difficult. So I think there's a lot of interest in providing introductory programming, and that's incredible, especially at the K-12 level. But we can't just get students excited at every group about these opportunities and then be like, okay, well, see you in 5 years when you get to undergrad, or make sure you go to a university that actually has a quantum program. We need to make sure that we're keeping students engaged through kind of their entire journey, K-12, university. And then when they're in the workforce, even if they're not in a field or area right now where they can contribute right away, you know, making sure we're keeping them engaged on latest developments and continuing to provide them skills. So when we are ready for them, either to be adopters and users or developers, we're there. And with that said, I'm happy to answer any questions. I know everyone's probably pretty hungry. If you would like to talk further about this, I've left my email, and I'm happy to chat more.
Questions, comments for Kiera?
This question comes from MAD Inc. 401, Inc. spelled with a K. How important is the practice and inclusion of the arts for a student studying quantum science and for the rapidly emerging academic quantum programs? How important is the practice and inclusion of the arts for a student studying quantum science and for the rapidly emerging academic quantum programs?
Yeah, so this is actually something I'm really excited about. We are in the process of developing a course for the humanities for quantum computing. I think for so long, STEM courses have largely been reserved for people who need technical knowledge, and we've left out policymakers, ethicists, you know, those who want to go into international relations. And so actually or even program managers and business leaders. So, you know, we are preparing a course actually that will be kind of suitable for everyone. I can't speak necessarily to the arts directly, but more just the humanities more broadly, and saying that I think everyone should be developing out a baseline level of skills and understanding of how quantum is going to impact industries.
Thank you, Kiera. Let's thank Kiera, Charles, and also Bob for this great session. And now it's time for lunch. So Vanita has some announcements.
Yeah, thank you to all the speakers in this session and all the sessions so far. So we've had a great couple of sessions in the morning. We're gonna break for lunch. I know you're all waiting for that. Lunch is on your own today. And so we have dining options, the restaurants behind the physics building on the northeast side of campus. And then there's also some of the dining halls, Butterfield, Main Fair, and some other dining halls that you can find on the campus map online. So feel free to explore those options. All right, so we'll be back at 2 p.m. for the afternoon session.